So good afternoon, everyone. Just before we start the next talk, just a reminder that if you could please ask your questions via the app, and then we can put them all to our presenters at the end. That'd be great. But please make welcome. We've got two international guests all the way from, I should say Luxembourg, but you almost say from France and from Deutschland, but it's actually close enough. So it's Michael Hamm and Christian Studer from Circle. Please make them welcome.
So thank you. So yes, I'm Michael Hamm, and I work at Circle. Circle is a kind of a national CERT for Luxembourg for the private sector. So we do much in incident response and forensics, but we will also do much in developing tools supporting incident response and forensics. So my main activity is in the incident response and forensics, digital forensics area.
Hey, I'm Christian. I'm also part of the Circle team for 7 years now. I'm mostly working on the development of MISP, the core platform, the interactions with different other formats, and some of the automation tools to automatically parse and extract data into MISP. So for today, I will be mostly giving support to Michael for this presentation.
Yes, exactly. As 2 days ago, we have the MISP training, which was led by Christian. Today, we have a forensics presentation, which is led by me and supported by Christian. So it works out like this. So the topic of today is, let's see, as we are many, the spooky USB stick. Yes. This is a topic developed at the Circle offices, and it's not really spread very wide. So there was a few, 2-3 presentations in Luxembourg, some local presentations at small events. So what we present today, you should not have seen it before. We also make some research, check the internet if it is known, and we don't find anything. So I hope it's new. You don't see it before. And the main motivation of this presentation is to show to you, sometimes you cannot rely only on your tools. Yes, sometimes your tool don't tell you the full story, and you should, as analysts, you should keep the capabilities to understand the data structures, to read the bytes, and so to figure out on a more low level what's going on. So motivation, keep on reading bytes, keep on understanding data structures. Don't rely just on tools and don't know what they do. So let's start with the USB stick. So I have the USB stick here. I connect it to the Linux workstation. It's a cheap USB stick. I hope it don't crash now. It works, okay. We have something mounted, and the device is called AUSCERT2024, which makes sense, and there are 3 text files on it. So let's check what we have. Okay, so we have some ASCII art on the file test3. We have some more ASCII art on the file test2, and we have some more ASCII art on the file test1. So that looks quite normal at this point. Now I will virtually hand over the USB stick to Christian, and he will connect it to a Windows machine.
All right, so now we take the USB stick, connect it to the Windows machine. All right, we open the USB stick. As you can see, also contains those 3 test files. But now, interestingly, when we open those files, it's welcome messages. What happens? Yeah, we will discover that later. Okay, so now I'm asking the question, what happens if I just add some modification here to the files? Are those modifications going to impact what's going on? So I will unplug the USB key and leave it to Michael again.
So let's check back if those modifications impact our files on the Linux machine. Oops, oh, egal. No, we have still the ASCII art, the other one, and the other one. So modifying the files on the Linux machine did not affect the files on the Windows machine, did not affect the files on the Linux machine. And I can tell you it is vis-a-vis, it's the same. I can make modifications here, save them, and we open up the USB stick in the Windows again, and we have the modifications of Christian back in the files. So now we are analysts. So we need to figure out what's going on. Somebody have some idea what first to do? I first would know how this USB stick is recognized by my workstation. So I plug it out. I go to the shell and start some dmask tool, -t, -v, just to figure out how this USB stick is connected to my workstation. Should presenter before. Okay, let's do it again. So we see it's recognized, yes. We see, we have a USB flash device, a general manufacturer, some serial number, USB mass storage device, and it seems to be recognized as device SDA, which makes sense. And it tells me that there is a partition SDA1 on it. Okay, that looks quite normal at this point. Okay, what can we do next? What about reading the partition table? That sounds like a plan. So let's fdisk -L and device SDA. So we get some output from the tool. It tells us there is a partition. Here we have the start sector, 140,000, and the end sector and the sides. At this point, my question, do you see something which already looks a little bit strange, maybe?
Is the capacity higher than, lower than the volume size? That looks like
the capacity is not very big, yes. It's a 9 gigabyte USB stick, and here we have a small partition of, I think, 57 megabytes. So it's a small partition. Yes, there's a... I cannot hear.
Sorry, normally your start sector would be lower, like 2048 or something like that?
Yes, that's a good remark. Yes, it looks strange that the partition don't start at very close to the beginning of the stick. It starts somewhere in the middle of the stick. So that's indeed a good observation, yes. And yeah, but more or less there's nothing suspicious at this point. And on the workstation we have another toolkit installed, the sleuth tool, the sleuth kit. So this is a forensic toolkit, and this toolkit also have a command to list the partition table. So let's use this tool to list the partition table. mmls is the command, dev SDA. So now I list the partition table of the device, and the output is empty. So that's scary, no, isn't it? The one tool say, yes, you have a partition table, you have a partition somewhere in the middle of the disk, and the forensic tool say, there's nothing, there's no partition table. That starts to get interesting, doesn't it? Okay, we access files, there must be something mounted. And the forensic tool say, no, there's no partition on the disk. So let's check what's mounted. Mount pipe to grep SDA. So what do we see? Yes, we have a device, SDA1, so we have the partition mounted on the mount point, Media Michael AUSCERT2024. So it gets more scary and more scary. We have something mounted, and the forensic tool says there is no partition on the disk. Okay, there's another little tool in the sluice kit. It's to reading the first sector of the partition to get information about the file system. Let's check this if there is some file system on device SD1 which is mounted. So fs dot def SDA1 pipe to less sub. Aha. So it seems there is a file system somewhere. We have an NTFS file system, we have a serial number, we have the volume name, it's maybe a version of Windows XP. We see we have 512 bytes per sector, and we have 4096 bytes per cluster. So the sluice kit tool, the forensic toolkit, which says there is no partition, says on the partition we have a file system. So that's funny. Okay. On the slides, we have screenshots for this scenario, and we have the commands. And now it's time to talk what's going on here. But before we talk what's going on here, we first must set the level to the same ground, so everybody should understand the basics. So we will explain a little bit background information. Let's look at the next slide. Look at the picture on the left side. I check, there are some young people around. Young people maybe received the idea that this is the 3D print of the save button. But no, it's a picture of a disk, a floppy disk, even of a modern version of a floppy disk. So, yes. Something which younger people maybe don't even know that it exists at one point. Okay, and on the right side of the screenshot of the screen, we see the structure of this floppy disk. Yes, so we see the floppy disk is split up in sectors. Sectors is the littlest addressable component on the disk. It's usually 512 bytes. And this is why it calls a block device, because you always address blocks of 512 bytes. So the sector is the littlest addressable unit. Or when you go a level higher to the operating system level, to the file system level, those sectors are very often connected together in forms of clusters. So the operating system, the file system, don't address each sector single, it addresses a cluster of sectors. So these are called clusters, and the complete circuit of sectors and clusters is called a track. In the picture below, we have the abstract representation of this disk. So you see it starts with sector 0, which is called the boot sector. And the boot sector have basic information like how many bytes per sector, how many bytes per cluster. That's what we basically saw with this tool. We get the label and stuff like this. So we get information mainly from the boot sector. So the computer needs this information to be able to work with this disk. And then behind the boot sector, we have the file system. And on the file system, we store our files with our content. So let's quickly take a look with a hex editor on a boot sector, how it looks. So it starts with 2 bytes, which is a very simple assembler instruction, and basically it's a jump instruction which says jump to the boot code. Yes. And the boot code of this disk is very simple because it's not bootable. If you try to boot the computer with this disk, it will simply display the message, this is not a bootable disk, and then maybe a beep and finished. Yes, here are some other information. For example, this 2 bytes, this is the number which says how many bytes per sector. So this is the 512 we see from the tool. And this 08 is how many sectors per cluster. So with this information, you can calculate that it is 4096 bytes per cluster. So everything is clearly defined, very good structured, and you could get all the information the tool showed to you, even by reading the hexadecimal representation of this information. For this presentation, it is very important that you realize after the boot code, there's nothing used anymore. So it's 512 byte, the boot sector, and just after 100 byte, the rest is empty, not used. Just to the end where you have a signature flag. And this signature 55AA, it's very common for all kind of boot sectors. It's always at the end 55AA for DOS formatted or DOS partitioned disks. Important, between the last 2 bytes and the boot code, it's empty. So that was about floppy disks. After a while, there was something more developed, which is more bigger. For example, the hard disks. And Chris will give a quick introduction into the hard disk.
All right. Sorry. Yeah, so with more modern disks, there are not so many differences. The way they work remains mostly the same. They still have sectors, clusters, tracks, and besides some of the differences, physical differences that we won't be detailing too much today, the main difference, as Michael said, is today compared to the previously used floppy disks, hard disks have a much larger storage capacity. And with the larger storage capacity, we can then have partitions with smaller spaces. So again, this is another abstract representation of a modern disk. At this point, it is unpartitioned, unformatted, mostly empty. So what we want to do in order to be able to store some data first is to create some partitions. So for partitions, we need a boot sector. On the disk, it's called the master boot record. It's the first sector of the disk. It will basically contain the partition table, and the partition table will describe each partitions with the information on where they start, their size, and so on. So now we have described our partitions. The next step we will be doing is to create some file system on each partitions. An interesting difference with the floppy disks, which is enabled by the fact that we have different partitions, is on this single disk. With different partitions, you can have different file systems, where on the floppy disk you have one partition, only one file system. We are not obliged to have the same file systems on each partition here. If you have been playing with partitioning tools and you're curious about how it works, sometimes you have empty spaces between partitions, empty spaces. This is mostly due to the fact that partitioning tools will always make partitions start at the beginning of a track in order to keep the physical alignment of the partitions on the disk. If they wouldn't be doing so, if they made the partitions start in the middle of tracks, you would be facing some performance issues. Right. So now we create our file systems on the partitions. Every file system, every partition has its own boot sector, as Michael showed before for the floppy disks. And as we already saw with his explanation, it basically is the first sector of the partition, and it contains the information on the file system, like the format of the file system, on all the different informations that have been shown already with the sizes and so on. Right, so now I will let you give more details on how a master boot record looks like.
I think you get it already. I like to work on the byte level, on the hexadecimal level of the stuff. So let's take a look how the master boot record looks on hexadecimal level. Again, everything is clearly defined. Yes, you see here that this master boot record is totally empty at the beginning, and just at one position, at close to the end, we have the we have the partition table starting. So I go here. The partition table starts at this bytes.
Oh, sorry.
I don't like presentation mode.
Sorry.
So here we have starting the partition table, and it goes until here, the end of the partition table, and then we have again those signature, which is very common everywhere on boot sectors. And so you see we have here 64 bytes, and this 64 bytes can manage 4 partitions. So this is the primary partitions. You can have maximum 4 primary partitions on a DOS boot, on a DOS partitioned disk. Okay, so here we have the start of the partition table, and everything is clearly defined. We have 16 bytes for each partition. The first byte, which is 00 here, tells, is the partition bootable? No, this one is not bootable, so we have 00. I think if it is bootable, you have 08 or something. The next 3 bytes are not used anymore today. They are for the classical addressing scheme CHS, I think. This is called. The next byte is clearly defined. It tells what do the computer have to expect as a file system on the partition. So here we have the 07. This means it's a Windows file system. It's NTFS or exFAT or something like this. I think for Linux, maybe you have 83 or 84. I don't know by heart. Okay, so the next 3 bytes are, again, not used anymore. It's the classical addressing scheme as CHS. And then the next 4 bytes, these 4 bytes, they are more important because it's the new addressing scheme, logical LHS or logical something. And it tells where on the disk, on which sector the partition starts. So this is very important. And here, the next 4 bytes shows the size of the partition. So with these 2 information, you can also calculate where the partition ends on the disk. So this information is basically stored in the partition table. And for this presentation, very important for you to recognize the partition table is at the end of the disk and the beginning, at the end of the boot sector, and the beginning of the boot sector is totally empty. And so maybe now you can get an idea what we had done. Yes, no idea?
Maybe you just wrote this sequence of bytes earlier in the boot sector and something picks it up and thinks that there's a different partitioning scheme on it.
Something like this, exactly. So let's look. We create something like a polyglot boot record. So first, we create a disk image which has the old classical style without master boot record, just one boot sector and the rest of the file system. This is still valid. You can still create a USB stick like this, connect it to your computer, and it will work out of the box. So we create a disk image looking like a floppy disk. And we put 3 text files on it, text 1, 2, 3. Then we created a second disk image, which is starting with a master boot record with a partition table and putting the partition somewhere in the middle of the disk. Then in the next step, we create a byte copy of the first version. So we make a new disk image, call it Legion, and it's exactly the same bytes like the first version of like the floppy disk image. And then I use the tool DD. You see the difference. I use the tool DD to copy the partition from the second disk image onto the new disk image. So now we have a floppy disk-like disk image with a partition on it. And now one point is missing at the end, the partition table. So we create the polyglot boot record by copying the information out of the partition table into this modified boot record. So that's how it looks at the end. So we have the modified boot record with the boot sector and the partition table. We have the 3 text files on the first version of the disk. Then we have somewhere in the middle of the disk a partition, which start with a boot sector and have 3 text files on it. And this is how it looks in a hex editor. You see, yes, we have this is now the boot disk at the beginning of the sector, and at the end we have the partition table. So it's a mixture out of both the stuff. And now it depends on the operating system, on the tool, what it takes. The one tool takes the boot record, the master boot record. The other tool takes the boot sector. The one operating system takes this and don't see the other things. The other operating system takes this and don't see the other things. So it totally depends how the software reads those initial sector and what it takes out of it. So that's basically the trick. So in the following slides, I have explanations step by step what we had done. You can reproduce your own spooky USB stick and scare your colleagues if you want. Just one disclaimer, take care if you work with a Linux machine, if you are a super user and you work with DD, don't do it on a production system because DD don't ask, DD writes. It's very easy to destroy your data. Just one wrong output device and it will overwrite your disk. So do it on a virtual machine, do it on a test system, not on your production system. Yes, but then you see simply you can go step by step through the procedures. You create first some files which you put on the one part, then you create some files which you put on the other part, store them somewhere, then you create the disk image. Here are the commands for everything. Then you create a second, or you add the first set of files to the disk image. You create the master boot record disk image, format it, and then you add the files on the second disk image. You can mount it. And then you create finally the polyglot image by copying the first, by using the DD to copy the partition into this new disk image, and to copy the master boot record information, so the partition table. And then at the end, you write everything to the USB stick, and if you don't make something wrong, you don't destroy your data, but you have your spooky USB device. So, are there any questions?
Well, before we have the questions, thanks for the talk, Michael and Christian. The first question we have actually is, have you analysed any of the Hack5 USB devices, like rubber duckies and stuff like that?
I don't understand. Can you repeat?
Have you analysed any of the Hack5 USB devices that appear as keyboards or other
A little bit.
non-storage?
A little bit, yes, yes. Indeed, what you maybe are not aware of, you can, on Linux, you can install a driver, and with this driver, you can sniff the USB traffic. Like you sniff the Ethernet traffic, you can sniff the traffic of the USB port, and you can follow the USB handshake. It's I don't know by heart, but it's maybe 8 or 9 or 10 handshake package, which sends forth and back. And at one point, you see, yes, hello, I'm a keyboard. And on some Hack5 tools, you see, yes, I'm a keyboard, and I'm a mass storage drive.
Another question, what are your favourite hex editors?
Or
It's a very religious question, I know, but...
yes,
Oh, sorry.
no,
It's a
I
big
have
question.
I have two favorite ones. The one is, I think it's, yes, exactly, it's Hexa. This is very, I prefer it because it's like VI, so you can modify the bytes and push the known keys from VI to save everything. And, but this tool has one disadvantage, it loads everything. So if you'd like to modify it on a disk, it tries to load the complete disk into memory, and that's not good. So for small things, for modifying files, I use the Hexa because it's like VI, and for the other things, for modifying the disk, I use the HexEdit because this only loads where you are into the memory. So.
Well, I guess there's... we probably should thank you guys for your talk. Before we do, actually, you should really check out the circle.lu website because they're very similar to AUSCERT in a lot of ways. They have a lot of services. They help their members, public and private. They're really big on collaboration. They've got some great tools. Obviously, everyone knows about MISP, but there's other actually really good online services. Michael and Christian are here all the rest of the week, so please make them welcome. If you see them, say hi to them. Hopefully be back again. So please thank these guys. Yes.